Welcome back. We are at lecture 40. My estimation that this course will be somewhere 60 to 65 lectures, I think, before we're done. So we're 2/3 of the way through the course, roughly. We've got our third test in just a couple days. We've got one more section of content to cover on Newton's method, or sometimes called Newton-Raphson's method of approximating zeros or roots of a function. So we'll cover that today. There is, I don't think when we did max man-word problems, we did justice to some problems that have endpoints. And they may not be obvious. They may not jump off the page at you. So let's take a look at a problem, at least to analyze how this particular problem has endpoints. And this is on page 312. And it is number 21. And when you read it, or when we read it, you'll think, gosh, I don't see any way that that problem has endpoints. But maybe somebody in here can come up with it. If not, we'll talk about how this problem has endpoints. Let me read the problem. A piece of wire 10 meters long is cut into two pieces. So we start with a piece of wire. 10 meters in length, cut into two pieces. One piece is bent into the shape of a square, and the other is bent into an equilateral triangle. How should the wire be cut so that the total area enclosed is a maximum? And then there's a second question to this problem, which probably tells you the other answer. One answer is going to come from calculus. The other answer is going to come from something other than calculus. Probably determining the endpoints. So here's our wire. We're going to cut it somewhere, let's say right here. And I don't know where that's going to be, so we're going to call it X. What's the remaining portion of the wire?
10 minus
Good, 10 minus X. And part of it, it says we're going to put it into the shape of a square. Doesn't really matter which part you take where. So if we take this piece, which is X, and form a square, what would each side be? 1/4 X. This is not drawn to scale. The other is bent into an equilateral triangle. So what is each side of the equilateral triangle? Okay, 1/3 of 10 minus X. And how should the wire be cut so that the total area enclosed is either a max or a min? So we actually want to maximize and minimize the area of these two. So we could figure out what the area of the square is. It'd be the side squared. Does anybody remember the area of an equilateral triangle? I think this came up in a problem before. Side squared times the square root of 3 all over 4. Maybe that didn't come up in a problem. Okay. So there's the area of an equilateral triangle. Area of a square is just side squared. So we could come up with a formula and then use calculus, set first derivative equal to 0. And that's going to give us one of these two. I don't know which, but it'll give us one of them. So what's going to give us the other one? Well, it's got to be endpoints. So what are the endpoints for this particular problem? Cut it in half? No? Good guess.
Would it be in the area that you can make with the whole wire?
Okay. It'd be using the whole wire. So in other words, the endpoints are, let me give you the, what if X is 0? That means that you cut it right here on the end, which means you don't cut it at all. So you take the left-hand portion, which is not very much, 0, and you form a square out of that. I'm not extremely talented, but I could do that. I could form a square out of nothing. The area of that square would be nothing. And if x is 0, then you put all 10 into the triangle, right? So this means 0 in the square, 10 in the triangle. Okay, what's the other endpoint?
10.
X is 10, which means you're going to cut it way out here at the end, which means you really don't cut it at all. And you put all 10 into the square and 0 into the triangle. So those become endpoints for this problem. One of them, these endpoints, is in fact going to give you the max or the min. And the calculus to it by taking the area here plus the area here, taking the derivative and setting it equal to 0, that'll give you the other answer. So it's probably not obvious all the time when you read it that problems really do have endpoints, but when you look at x equals 0 and x equals 10 on this problem, I think it becomes a little more clear that those really are not endpoints, but a beginning point and an ending point. So your graph, if you were to graph area, it might look something like this. So 0 and 10 are candidates for max and min. The max, I don't know if this is the case on this problem, the max actually occurs at the calculus, where the derivative is 0. The min actually occurs at the endpoint when x is 0. I don't know that that's what it looks like, but that's a similar situation to what we're dealing with in this problem. All right, any last second issue with max-min word problems that would take just a couple of minutes to diffuse or dissect? So you're experts.
There was one on the left side. I don't know if anybody has it. It's the one where like it's a cardboard piece of box that's 3 inches, and you have to cut out
The squares.
inches and fold it up.
Okay.
Like I've done problems like that before, but I didn't.
I think we can do that in a couple minutes.
Okay.
So you want to maximize the volume, is that right?
I was confused because it wanted you to like write something in terms of why. Like it wanted you to write.
Which one is that?
Number 3.
3. You want to read it?
I don't have the
Here.
words. I just have the words.
Okay. Find the dimensions of a rectangle with area. Is that the right problem?
Yeah. Is it?
Dimensions of a rectangle with area 1,000 square meters whose perimeter is as small as possible. Okay, I think we in fact did a problem like that.
It's,
One after that?
It's like you
Box
have to,
with an open top is to be constructed from a square piece of cardboard?
Yeah.
Okay.
Yeah, where you cut it.
All right. So this is 3 feet. I don't know if that's the same in all problems, but that's the way it is on this problem. So that might change from one problem to another, the dimensions of the square piece of cardboard. Cutting out a square from each of the 4 corners, bending up the sides. Find the largest volume that such a box can have. Let x denote the length of the side of the square being cut out. Let y denote the length of the base. I don't know that we need to kind of start with 2 variables or not, but let's. So we're going to cut something out before we get the scissors out. We'd kind of like to solve the problem. So we're going to cut out x by x. Out of each corner. And we'll take that and cast that aside. So this is waste. These, which may be part of another problem, is that, consider that as part of the problem because it's part of the cost involved, but it's not part of this problem. So with what's left after we cut an x by x square out of each corner, we're going to crease it right here, right here, right here, and right here. And we're going to fold those sides up. So we're going to have a box that doesn't have a top. That hopefully is a little better than my diagram here. How tall is that box when you cut x by x out of each corner and fold up the sides. It's x tall, because this is what actually gets folded up, right? This distance, when you fold up those sides. After you fold up all the sides, you lose x from each direction as you fold x up, and so you really are dealing with what, 3 minus 2x right here? And as you fold this side up and this side up, there's the real dimensions kind of what's left of the box, which is 3 minus 2x. So this is 3 minus 2x. So is that okay? Everybody feel comfortable with that?
How'd you get the 3 minus 2x again?
It was 3 from here all the way to here.
Oh, okay.
And as we fold this side up, kind of envision this side going up, and we're going to fold this side up, we lose x in each direction. So it's from here to here. So if you lost x in each direction, it's now 3 minus 2x. Same thing for the other side. So the volume is that. Is that all right? Length times width times height. What did the problem say? We want to maximize the volume?
Yeah.
Is that right? So there's our volume function in terms of x. We don't need to make any substitutions. It's in terms of a single variable. Let's go ahead to this product, which would be 9 minus twice their product, which is minus 12x plus 4x squared. Is that correct? So there's our volume function. You could call it v of x. And what happens then to complete this problem?
Take derivative.
Take the first derivative, set it equal to 0. This problem has endpoints. That's probably pretty good that we look at this one as well. What are the endpoints? What's the least you could cut out of each corner?
0.
0. If x is 0, you cut 0 out of each corner, which means you still have this piece of cardboard with no cuts and nothing to fold up. If you fold up 0 on the sides, which kind of sounds absurd, how tall is the box? It's 0 tall. And what's the volume? It's 0. So when x is equal to 0, the volume is equal to 0. You can't get any smaller than that. So the volume is 0. What's the other endpoint?
3.
Oh.
Or 1.5.
1.5.
Because if you cut both out.
There you go. Because it's only 3 on each side, right? And if you come here 1.5, that leaves 1.5 for the other one. So if you cut a 1.5 square out of each corner, there's not a whole lot left of our piece of cardboard, is there? In fact, there's nothing left. So the other one is 1.5, and when x is 1.5, the volume is also 0, and you can't get any less than 0. So the real answer is somewhere between those two values. If you get a value that's larger than 1.5, that's absurd. You can cross it out. Even though it might solve the calculus or the algebra, it doesn't solve this problem that's associated with it. So we want the realistic answer that's somewhere between 0 and 1.5. We know how to get a min. Now we want to use calculus to get us a max. Is that okay from that point, Nicole?
So once we take the derivative of that and we set equal to 0, when we get the point, we put it back into the volume equation before the derivative?
You would get an answer in terms of x, right? So x equals something.
Mm-hmm.
I don't know what it's going to be. Let's say it's, I'm just guessing. Let's say it's 2/3. Is it realistic? Yes. Somewhere between our kind of our two endpoints, which are somewhat realistic, but they're also a little unrealistic. Depending on the question, if it said, what are the dimensions? Well, there's 2/3. Put 2/3 into this. There's the other dimension, and put 2/3 in for x for that. If it said, what's the volume, then you'd take 2/3 times whatever this number is times whatever that number is, in cubic, whatever this is, feet. The one thing we haven't done yet is that we would have to take v double prime at this particular x value, whatever it is, 2/3, 3/4, and we would want that to be what? We want this to be a maximum. We want it to be concave down, which is negative, right? So we'd have to validate that. Is the second derivative at this particular x value, is it negative? If that's true, it would be concave down. Therefore, we have a max. Does that work for that one? So if you had the dimensions at 3 feet by 3 feet for the piece of cardboard, there's the function. You're going to use calculus on that function to determine where it's the largest that it can be. See? Perfect timing. Okay. Newton's method, the last section of content prior to this test. Now that is for this class that's physically meeting here. There's a chance that on cable TV or certainly on DVD that the places where we stop and start the course to have test 2 and test 3 are different. So make sure if you're taking this course on DVD that you check the pacing guide that's provided, because it may not be that this is the last section of content before test 3. So I know you're getting tired of hearing that in this class, but that'll save me from getting 30 emails saying, well, you said on the tape that the test ended with 4.8. That's for these folks in the classroom. Newton's method, you would expect that to carry a little bit of weight because of the name of it, Newton's method, rather than Jones' method or Smith's method. I mean, Newton, you think that's probably pretty significant. It's useful for, and it does use derivative, it's an application of the derivative. That's why it's here in the text. We are going to use first derivative to help us find the roots, or if you want to call them zeros, of a function. So how do we use Newton's method? If we have a picture, then we can make a reasonable guess. And it doesn't have to be necessarily a very good guess. Sometimes it's given to us. Okay, x0 is such and such, or x1 depends. On this book, they refer to that as x1. So it is not the root of the polynomial, but it's close to it, and it's going to hopefully get us a better answer with this iterative procedure. So I have a better picture, and this one's going to get cluttered very quickly. But let's say our graph looks something like this. So there's our function. We're looking for the place where this function, crosses the x-axis. So we're looking for the root or the zero of the function. So we guess, we're going to do better than this, or hopefully they're going to start us out better than this. But let's, for purposes of the diagram not getting cluttered very quickly, we guess that our root is actually x1 when it's really over here. Okay, it's really 1.7, but we guess 2. That's our initial value. Here's the iterative procedure. So we go up to the curve. We locate that point on the curve. So we're at the point x1, y1. We construct the tangent line to the curve. Could we determine the equation of that tangent line? We know a point on it. So the point is x1, y1. And what's the slope of the tangent line?
Derivative of the function.
It's the derivative of this function at that point, right? So it's the first derivative of x evaluated at the specific value x1, because that's where we are. We're at x1. So if that's the information about the tangent line, we could certainly find the equation of the tangent line. By the way, once we get this pattern, you don't have to do this over and over again. So the equation of the tangent line is what? How does that go? We know a point and the slope.
Y minus y1.
Y minus the known y value. What's the known y value?
Y1.
It's y1. I'm going to go ahead and call that f of x1. Is that all right?
Mm-hmm.
Y1 is really f of x1 equals, so that's y minus y1 equals
M
slope times
x minus x1.
x minus the known x value. So there's the equation of the tangent line. Now, what do you think the procedure is going to be? So we're going to draw that tangent line, hopefully quite a bit straighter than mine is drawn. It will cut the axis at a point. Let's call that x2. We'll start the process all over again. We'll go up to the curve. We'll draw in the tangent line to the curve. Told you this was going to get cluttered in a hurry. Where that blue tangent line crosses the axis should be even closer to the root. So you keep working your way in using the tangent lines. Now this can fail. This process can fail, and maybe you're thinking about how it might fail graphically. But we'll talk about the ways that this process can fail. But you keep working your way in, getting the point of contact with the axis, go back up to the curve, draw the tangent line. In fact, I've got a diagram that's not quite so cluttered as this. We'll come back to this. But here's a diagram that's better. So here's our starting point. Here's our starting point on the curve. We construct the tangent to the curve. Where it hits the axis is our new value, kind of our new guess. X2 is our new guess. We come up to the curve, construct the tangent. Where that tangent line hits the axis, that's our new and improved guess. We go up to the curve, draw the tangent line, and you keep going with that process till you get closer and closer to the actual root.
How do you know when to stop?
You'll be instructed to find the root to, let's say, 2 decimal places. So when you see those 2 decimal places in this iterative process, you see the one answer is you get 0.261. Then the next one is 2605. And the next one is 26. In other words, when you see them not changing anymore,
Yeah.
then you're good
Oh, okay.
to that level of accuracy. So is the process on the diagram, is that reasonably clear? So we're going to take this first tangent line, which we know the equation of that. I'm just copying this from the bottom of the previous page. There's the equation of that first tangent line by using the point x1, f of x1, and the slope, which is the derivative evaluated at x1. So we come down here on that line, that tangent line, and we locate this point, which they call x2. Now that actually has what coordinates?
X2, Y2.
x2, 0,
Oh, 0.
right?
Yeah.
Are the coordinates of that point. Isn't that point also on this line?
Is it?
So doesn't it have to work in this equation?
Yes.
So the point x2, comma 0 works in this equation. Why does it work? Because it's a point on the line. Every point on the line actually solves the equation. So for y, we'll put in 0. And for x, we'll put in x2. So instead of y minus that, we're going to get 0 minus that. And instead of x minus x1, we're going to put in what is the specific x value of this point. It's x2. Now, I'm not going to have enough room to do that, so let's move this to another sheet of paper. Any questions about us getting to that point in this equation? Yes, Chandler.
So you don't do the y minus the new f of x.
Right. I just put it in. If you had an equation for a line, let's say 3x plus 2y equals 11, and you knew a point that was on that line, how would you validate that that point is in fact on the line? You'd plug the new x in for x and the new y in for y and see if you can't take 3 of the x's and 2 of the y's and add them together and get 11. Okay. So it's kind of a validation that this point is indeed on this line. It has to work in the equation. Jonathan?
And you'd find x2 by setting y equals 0? How would you find x2 without graph? If you were just...
You could take the equation of this line, and in fact, we're going to kind of do that. That's what we're going to do, is we're going to say, okay, how do you actually determine what is x2? I think that's what Jonathan's question is.
Right.
You could basically put in 0 for y and solve for x2. That's, in fact, our next step,
Right.
is how do you get this? We started with x1. Either we guessed or they give us something to go with. We want to use the process to get a better approximation of the root. How do we get this better approximation? Let's do that now. So let's take this equation. I'll move it to another sheet of paper, and we want to solve it for x2. So what would be the first step in solving? This is still the equation of the tangent line. We want to solve it for x2. How do we get this next best guess at the root of the function?
Move over f prime.
Divide by f prime, right? So this side is just 0 minus that is just minus this. So I'm going to divide this side by f prime of x1. And I'm going to divide this side by f prime of x1, which leaves what? x2 minus x1?
And then add x1.
So we divided this side and divided that side. So there's our new equation. It's one step closer to solving for x2. What else? Add x1 to both sides.
Mm-hmm.
So we get x2 over here. Here we get x1 minus f of x1 all over f prime of x1. So what was x1? x1 was our initial guess, right? So if we take our initial guess, we subtract from it the function at the initial guess, divided by the derivative of the function at the initial guess. All that is stuff we should be able to do and do that particular configuration and pattern, and that should give us x2. So we don't need a diagram. All we need is what happened here. Somebody that sees the pattern, tell me how we would find x3. We would take x2 minus the function at x2 divided by the derivative at x2. So your answer to part 1 becomes your data to part 2. So you were searching for x2. Now you have it. It becomes your data as you search for x3. Everybody see the pattern for Newton's method? If you want x4, the next best guess at the root, x3 minus f of x3 all over derivative at x3. So it's this iteration, this iterative process. Or, in general, if you want to find the next x value, you want to find x sub n plus 1, what do?
X to n.
What's the previous value?
N.
X sub n. Give me the rest of it.
Minus f of x to the n.
All over
x
f prime
prime x.
of x sub n. So you haven't written anything down yet today. That might be a good thing to write down. That actually is Newton's method. But you do have to have either we pick off a point or we have to be given a starting point. Now, I told you that it could fail. Did anybody, can you think of how this could fail?
The derivative is 0.
There you go. Okay. Anytime you have division within a problem, you ought to be looking at what's in the denominator. And if that were ever 0, we'd be in trouble. So if the derivative at x sub n is 0, this is not going to work. Tell me what the picture looks like there. It's flat.
It's flat, yeah.
So here's what we would be trying to do. So the derivative, we come to our guess, there's x1. We come up to the curve. The derivative is 0. What do we want this tangent line to be doing? Don't we
Crossing
want it
the
to come
x-axis.
back and cross the axis again? It's not going to. So it confounds the whole process. That's why when the derivative is 0, it's not going to work. Not only does it mess up the arithmetic, because you're trying to divide by 0, it messes up the whole process of what we're trying to do with this iterative process. So if the derivative at an x value that we choose is 0, all right, let's suppose that you choose an x value and the derivative is 0. It's not going to work. What do?
Choose another x.
Choose
value.
another one. Okay. So if you have an idea what the graph looks like, come back in here, choose this one. This one, by the way, is a little different. So your derivative comes in here. Notice the second value. Sorry, I called that the second. This is now the third.
We start
It's on
adding.
the other side, right? So you would come here, draw the tangent. Then you come up here and draw the tangent. Notice they kind of go back and forth. It kind of depends on the shape of the graph. The first one we did, they closed in all from the same side. It is possible to close in from alternating sides of the root.
Would that change the equation?
The equation changes only because the shape of the curve sent us further on the other side of the root. It's the shape of the curve which is certainly related to the equation. Now, I don't know if this gets another way that this can fail, if that brings it to mind. This type of diagram certainly makes me think of a second way that it could fail. So here's our first way that it fails.
If it's the vertical, right?
If it's undefined.
If it's undefined,
Yeah.
it's going to fail. So let me write that down. Because it's hard to put something undefined into an equation, so we're going to have trouble with that. See if I can make a diagram where this is. So let's say that got some symmetry going on here. And we come over here and we guess at this first root. So we're really looking for this point, but we guess right here. We come up to the curve. We draw the tangent line. it sends us over here. So here's our next best value,
It's just going to send us right back.
and it's going to send us right back. So there is a chance, this is actually a smaller chance of happening, that you could end up in a loop that doesn't really iterate itself any closer to the root, that these tangent lines are parallel, and it sends you back to the first value. So you're stuck. You're not going to get any closer to the root. So this could happen, where your tangent lines are parallel. And we're not going to find the root by iterating. I guess here's a fourth way this could fail. Here's what you're looking for, and you make a real bad guess, or somebody tells you a bad value, and you come out here, and it starts to send you to another root that's out here somewhere. So it's actually sending you to a root, but not the root we're looking for. Again, picking a value closer to the actual root, this root, will get you going. So it has its ways of failing, but for the most part, it's going to work for us if we don't fit into any of these kind of somewhat strange situations. All right, a couple of examples. Here's our function. Start with a polynomial. They are actually giving us an initial guess that's supposed to be reasonably close to the actual root. So you might want to find the derivative before you get started, because we're going to need it, right? Derivative of this polynomial is minus 2x. So I've got x1. I want to find x2. So I want x1. What's the rest of this? Question, Jonathan.
Would it be smart when you take the derivative to go ahead and set it equal to 0 and know what values to avoid?
Right. You might just see if 1, when you plug 1 in, if it causes it to be 0, because then this is where they gave us 1. I don't think they're going to give us 1 where that's the case. But when we're guessing ourselves, you might want to say, okay, what does 1 do in the derivative? Is it 0? 8 seconds later, you can tell that it's not 0. What's the rest of this? F of x1 over f prime x1. So I would kind of have that memorized for Friday's test. So we're looking for x2, so it's x1, which is 1, the function at 1 over the derivative at 1. What's the function at 1?
1. Oh, I'm sorry. Negative.
1 cubed minus 1 squared minus 1? Negative 1?
Negative 1, yeah.
And what's the derivative at 1?
1.
1? So x2, which is supposed to be a better value, what is it?
2.
2? Do you think the root is actually somewhere between 1 and 2?
Yes.
Do we have a way of determining that? What's the
graph.
f of 1? What did we get for the f of 1?
Negative 1.
Negative 1. We're going to have to find the f of 2 anyway if we go any further. What's the f of 2? 3? Is that right? Does that mean that there is a root somewhere between the x value 1 and the x value 2?
Yes.
Gosh, I remember something about that. What's that called?
Intermediate value.
Good. Intermediate value theorem. And this is only true if the function is continuous. It's a polynomial, so it's continuous. So we know the root is somewhere between 1 and 2. If you had to guess, would you say closer to 1 or closer to 2?
Both of them? No.
Well, the f of 1 is negative 1. The f of 2 is 3.
Closer to 1.
Maybe closer to 1. All right, let's go on with the process. We have x2. So we want x2 minus the f of x2. You can have fewer steps than I'm writing, and I'm going to shorten the steps here as we continue, but it is the first example. So x2 is 2 minus the function at x2.
3.
We said already that was 3 over the derivative at x2. 8?
8.
Is that right?
Yes.
Okay, you know at some point in time if it's between 1 and 2, I mean it's not going to be 3 halves. So we're going to end up with a value that's not delightful to work with. 2 minus 3/8. 13/8. All right, now the fun comes out. You want to make sure you have your calculator handy. So if we want to find x4,
Really?
so it is 13/8 minus the function at 13/8 over the derivative at 13/8. That sounds like fun.
Oh, yeah.
Somebody put 13/8 through the function. 0.65 is the numerator. 6504. Somebody throw 13/8 into the derivative.
I'm quickly see what that was.
3.
I mixed it up.
I got 4.672.
Same? Both of you? 4.672. So if we take 13/8 and we subtract that quotient,
Mm-hmm.
1.486.
so where do we know for an absolute fact the root is trapped between what two values now? Aren't we going back and forth? We went from 1
2 and 1.
to 2, so the root is actually somewhere between 1 and 2. Now we should be back on the other side with 13/8. So isn't it somewhere between 13/8 and 1.468?
Mm-hmm.
The root is somewhere between those values. If we were to continue, obviously on a test, this would be more than sufficient, because the important thing that I want you to know is that when you find x2, you're going to use x2 to find x3. So your answer becomes your data kind of for the next step of the problem. That's been accomplished. So without taking all the time on the test for all kinds of computation, x3 is probably as far as I would have you go on a test, just for time purposes. So you're either going to have to be told that, or you're going to have to be told a certain level of accuracy that you could go with. Again, you know that if you were to continue this process and you would see the 4 and the 8 lock in and no changes ever happen, then you know those are good. You're good to those decimal places that cease to change as you continue the problem. Let's start this problem, and then we'll continue it. We want to use Newton's method to find. This is a little. It doesn't seem like Newton's method's going to get us what we want here. We want to find the cube root of 4 using Newton's method. I thought we had to have a function. Right? Isn't it the function minus the function at a value over the derivative at a value? So this must be the root
of the function.
to what? What function? What function could we set up such that the cube root of 4 is the solution to that function?
Cube.
X cubed
X cubed, yeah.
minus 4
Minus 4.
equals 0?
Yes.
Is that the equation? You kind of make your own equation so that this is the solution to it. Is the cube root of 4 the solution to that equation? So our function is x cubed minus 4. And our derivative would be what? 3x squared. And you say, well, what's the cube root of 4? I don't know. Give me a guess. Give me a whole number guess. 1.5?
Yeah.
Do we know it's somewhere between 1 and 2?
Yes.
How do you know that?
So if it was 2.
Because 1 cubed is 1, and 2 cubed is 8, and we were looking for something cubed that'll get us 4, right? So it's got to be somewhere between 1 and 2. You could start with 1, you could start with 2, or you could start with 1.5. So we'll start tomorrow with 1.5 and see if we can find a reasonable approximation, just with a couple of iterations, for the cube root of 4. We'll see you tomorrow.